This is section 8.1, and we're looking at the dot product and basis vectors. I think that's kind of it probably for this video. So we know what the dot product is. This is just extending it to 3 dimensions. So if we have an x vector that's x1, x2, x3, and a y vector that's y1, y2, y3, then if we do x dot y, we just have x1, y1 plus x2, y2 plus x3, y3. So, and again, we could take this to 4, 5, 6, 10 dimensions, doesn't matter. And again, we have the norm, the 2 norm. We've seen norms before. So the 2 norm, I'll drop the 2 in the future, but just to, so we realize there's more than one possible norm, but the 2 norm is our x1 squared plus x2 squared plus x3 squared, but that means that is also the square root of x dotted with itself, and then there's the Cauchy-Schwarz, inequality. And again, I've mentioned inner products. This is an inner product property generally, but if we take the absolute value of x dotted with some y, that's less than or equal to the norm of x times the norm of y. Okay, so that's a very nice inequality, and again, because of that idea, then notice that if you take x dot y divided by the respective magnitudes here, that's always less than or equal to 1, and therefore what we do is we define our cosine of theta, or the angle between 2 vectors, as whoops, not the absolute value, sorry, let me get rid of that. Okay, as the dot product of the 2 divided by their respective magnitudes. And of course, this is for non-zero vectors, because I can't divide by 0. So so that's how we find an angle between 2 vectors. And again, this geometrically for 3 space, this is true. It really is the cosine of theta if we measure that angle. But more generally, we can define something like this to talk about the angle between 2 vectors, even when the geometry itself isn't physical, isn't something we can really see. And let's see. Then we also have the triangle inequality. Oops, I must have gotten off writing. There we go. So the triangle inequality says that the norm of x plus y is less than or equal to the norm of x plus the norm of y. And so this is the triangle inequality. And the reason it's called the triangle inequality is geometrically, right? If I take a vector x here and I add to it, well, that was kind of cool. Somehow I snapped that into a straight line. Not sure how I did it. And then and I add to it the vector y, then this is the vector x plus y. And so really, it's called a triangle inequality because it's saying, hey, if I take any two sides of a triangle, they will add to be bigger than the third side. And so that's what we see here. And, so we have this nice triangle inequality. And that actually, if you know you have the Cauchy-Schwarz, then I think the triangle inequality is usually pretty straightforward. I guess if we start, let's see if I can do that off the top of my head. Usually you want to start with square and show that the square is less than the square over here. And the big deal is the way to usually make it easier is to use Cauchy-Schwarz inequality. So what I'm going to do is take x plus y dotted with itself to get the square of that norm. And so using our properties of the dot product, you get x dot x plus 2x dot y plus y dot y. Now, there is something to be said here about the 2x dot y, because when you look at this, you actually get an x dot y and you get a y dot x, but we know that the dot product is commutative, and so I can write those in either order, and so that's what I do. Okay, and so now we could do minuses as well and have this be true, all right? And so well, let's see. So what I want to do is compare this to. I might have to. Oops. I might have to start on the other side now, just to kind of think of what I want. So on the other side, so let's do that. Right on the right hand side, I have the x norm and the y norm added together, and I want to square those. So see, in this, when I'm doing a proof, I might have to kind of work from both ends sometimes because I just don't remember exactly what I want. So the x dot x is going to come from here, multiplied by itself. The y dot y is going to come from there, and so yeah, I'm going to get 2 times the norm. Okay, so I see it now. Okay, what we can now say is this is x dot x. So I didn't actually have to write out what this was. We'll get there in a minute. X dot x, I'm going to say this is less than or equal to, and then plus 2 norm of x, norm of y, plus y dot y, or the norm of y squared. So So there's my less than or equal to. Here's equals. And this is equal to the norm of x plus the norm of y squared, right? Because I'll get the norm of x squared, which is x dot x. I'll get the norm of y squared, which is y dot y, and then I'll get the mixed term of 2 times these things. So I have that. And again, whether I use the plus or the minus, the Cauchy-Schwarz inequality has an absolute value on that, so I'm all set. And so there's our proof of the triangle inequality. So we have that, and let's see. Okay, so then that just leads us to again, this idea of orthogonality. Okay, x and y are orthogonal if x dot y is equal to 0. Okay, again, that's just an extension from the two-dimensional case in chapter 7. And so then finally, again, we can talk about bases. Well, here it is very typical to name this vector, the standard unit vector in the x direction, as I, the standard unit vector in the y direction as j, and the standard unit vector in the z direction as k. Now, you could call these E1, E2, and E3. That happens as well. Whoa! Let's see. I think I just need to hit there. Yeah. Okay. Oh, I probably hit my thumb up in the top left corner up there. So, okay. So we have our standard unit vectors here. They form a basis, and so any x, x, an element of R3, I can write as x equals sum A times I plus sum B times J plus sum C times K. So any vector in R3 I can write as a linear combination of the standard vectors. And I guess since we have orthogonal, we can also mention parallel. X X is parallel to Y if X equals TY for some real valued T. And again, geometrically, that's definitely true, but that also comes from the idea that if X equals TY, then if I were to take X dot X dot Y over the norm of X, the norm of Y, then what I get is T times Y dot Y over the absolute value of T times the norm of y times the norm of y when I make that substitution for x. But the top is the norm of y squared, the bottom is the norm of y squared, and so I get t over the absolute value of t, which is equal to plus or minus 1. But this is cosine theta, so we have cosine theta is equal to plus or minus 1, which implies theta is equal to 0 or pi. Okay, so the angle between them is either 0, so they're going in exactly the same direction, or the angle is pi, so they're going in opposite directions. Okay, and I think we'll stop this there.